Okay, so let's get kicking with our homework assignment. Everybody can see my screen being shared. All that looks good-ish. All right. So I have the chat up on my screen, so there's a decent chance I might see it possibly, but otherwise, as usual, just blurt something out if you have something to blurt out. I'm still waiting to hear back from our speaker for the tech talk in April, so I'll let you know as soon as I hear back from her. I guess it's a little concerning she hasn't responded yet, but as of right now, we're planning on doing that over Zoom, but if that changes, I will let you know. Okay, so let's look at the homework assignment. So for today, we were supposed to add some stuff to our fraction class. So we want to give fractions the ability to add themselves to another fraction, returning a brand new fraction, which is the sum of those two fractions. All right, so let's kind of look through this. If you noticed yesterday, I mentioned last class, make sure you're checking Slack often, because now that's our primary way of communicating besides Zoom. I was meeting with some students yesterday, and they were asking some questions about this assignment. So I gave them, we kind of worked through some examples here, and I put that code up so everybody else could look at it if you were wanting to. The main confusion, which is normal when you're first getting into object-oriented programming, is this idea of a fraction. So for instance here, let me just kind of walk through this code real quick to explain what it's doing, and then we'll modify it to get us to our solution. So I'm creating a whole bunch of fraction objects here. So the idea of having a fraction class is that we can now conveniently represent, in our case here, we're representing fractions, mostly because they're relatively simple. They only keep track of a couple of pieces of information, 1/2, 3/4, 7/14, that kind of stuff, rather than keeping track of 50 different pieces of information. But we're using the fraction class too. So this is how we call the fractions init method. So this automatically, so this method is named something very specific, underscore init underscore underscore. It has a very, very, very special name, so that when I call the fraction class like this, it automatically knows which method to call. And if we notice up here, our init method takes two parameters, a numerator and a denominator. All right. Down here, I'm giving it a numerator and a denominator, a numerator and a denominator, a numerator and a denominator, so on and so forth. All right. So every single time I create a fraction, I provide it with a numerator and a denominator, and this guy will make me a fraction and return for me the memory address of where that fraction lives. All right, we saw that last time. If I say print F1 here, and I run this, notice we get a memory addressy thing. Actually, that's with result. Here's F1. All right, so when I create a new fraction using the constructor, it builds for me a fraction. This is a fraction whose numerator is 1 and whose denominator is 2, and he returns for me the memory address where that fraction lives. And I'm storing it, in this case, inside of F1. This next line, I'm creating another brand new fraction, a completely separate fraction. This one has a numerator that's 3 and 4. A numerator is 3 and a denominator that's 4. It's going to return a memory address, and I'm going to store that in F2. Similarly with F3 and F4. So I have 4 different fractions here, and I have 4 variables, F1, F2, F3, F4, which each hold the memory address where each of those individual fractions live. Okay, this is the same thing as if I gave you the address of my house, and my neighbor gave you the address of his house, and one of my friends gave you the address of his house. So I'm giving you the address of a fraction. And if you want to interact with that fraction, you have to go to that address. And if you want to call the open garage door function, you would have to go to the address and tell the garage door to open. Excuse me. Not Corona, just went down the wrong pipe. All right. So in any case, we have a bunch of fractions. And now for our homework, we were supposed to create a function called add fraction that takes a fraction as a parameter. So let's look at add fraction here. So here's add fraction. This is a method that belongs to the fraction class, which means every single fraction, every instance of the fraction class will get his own version of add fraction. Instances of fraction are like F1, F2, F3, F4. Technically, those guys hold memory addresses which point to instances of fractions, but we would say that F1 is an instance of the fraction class. We would say F2 is an instance of the fraction class, F3, F4 as well. So F1 would have his own add fraction method. And F1's add fraction method has a variable called self that knows about F1's numerator and F1's denominator. F2's add fraction method has a variable called self that knows about F2's numerator and F2's denominator. So self is how an object refers to itself from within itself. So if I am calling one of F1's functions, inside of that function, when I say self dot something, we're talking about F1's stuff. If I'm calling one of F2's functions, inside of that function, self refers to F2's stuff. We don't have access to this variable called F2 inside of add fraction here. Instead, we refer to it using self. When F2 is calling one of his own functions, inside of that function, he can talk about himself using the self keyword. Okay? So in my example here, I've created 4 fractions, and then I went ahead and I said, well, let's go ahead and have F1. So we call this the calling object. So F1 is calling his add fraction method. And we're passing as a parameter to this guy, F2. Here's add fraction, add fraction. Remember, all of our methods take self as that first parameter, so we don't count this as required parameters. It's not something we pass in, it automatically happens. All right, so this guy takes a single parameter. I've named it another fraction, implying that I expect them to pass me a fraction. All right, so down here, F1, which is a fraction, is calling his add fraction method, which expects us to pass it another fraction. So I'm passing it F2, which is a fraction. So in that particular example, inside of this add fraction method, which in this case is owned by F1, right? F1 is the guy who called his add fraction method. F1 dot add fraction. He's the one that called his add fraction method. So inside this particular example, self refers to F1. Another fraction refers to F2. All right? Questions about that? That gets us about 3/4 of the way home if you can connect those dots and understand those pieces. Because I know we've been driving this point home in the last several classes, but this idea of understanding that variables have values, and we might have a variable name that's associated with a value outside of a method, but once it gets passed as a parameter to a method, it's the way we access that value is often through another variable name because it gets passed in. We are passing F2 in as a parameter to add fraction. F2, his scope only lives inside of main. We don't have access to that variable someplace else. So once I hand F2 as an input to add fraction, he's coming in as something called another fraction. So my way to refer to him from that point forward is by saying another fraction for as long as we are inside of here. That's how we refer to, in this particular example, F2. And in this particular example, the way we talk about F1 is through self. All right, so we're kind of proving this example here by printing out another fraction's numerator. So whatever fraction was passed in as a parameter, we're going to go ahead and print out his numerator. And whoever called this version of add fraction, we're going to print out his numerator. All right, let's just start off with those two pieces. So I'm going to take off this printf1 thing here. So in this case, I am having f1 call add fraction, passing it f2. And the first thing we did in there is call another fraction. We printed another fraction's numerator. So the first thing we should see print out is f2's numerator, which is a 3. The next thing we do in there is we print out self's numerator. And the guy who called this add fraction function was f1. So self's numerator is a 1. So we should get a 3 printed, then a 1 printed. And actually we get a 3 printed and a 1. Actually, the second time around, we'll get a 7, we'll get a 13 printed and then a 7 printed, because notice I'm calling add fraction a second time here. But in this case, self will be f3 and another fraction will be f4. I'm passing it different parameters. All right, so the output here should be 3, 1, 13, 7, and then we're printing out the value of result, which returns from add fraction. And if you notice up here inside of add fraction, I was showing them how to build a brand new fraction inside of there and then return that answer. So this is how we build fractions. We build fractions this way. It calls the init constructor for our fraction, building a new fraction that has a numerator of 4 and a denominator of 16, and then we're returning that guy. So that's what gets returned into this variable here called result. And then I'm printing out result, which we already saw earlier is a memory address, because whenever I create a fraction, the value that it boils down to is the memory address where that fraction lives. But I can then call that particular fraction's function. So in this case, I'm calling his display function right here. And this display function takes no parameters, so all it knows about is the guy who called it. And we're printing out that guy's numerator and denominator. And if you notice in add fraction, I just hard-coded a numerator and denominator for our fraction, 4 and 16. All right, so we should get from this line here, it should print out a 3 and then a 1. From this line here, it should print out a 13 and then a 7 and return for us the value of result. Notice I didn't capture, we did get a fraction up here, but I didn't store it anywhere. I just chose not to use the fraction that was returned from it. But here we're going to, as part of this add fractions, it's going to print out the numerator of f4, which is 13, the numerator of f3, which is 7. Then it's going to return the fraction. I'm going to print out the value of that fraction, which is a memory address. And then I'm going to use that fraction to call his display method, which should show his numerator and denominator, which is 4/16. So there's our 3, 1, our 13, 7. Here's the memory address of result. And then here's result calling his display method.
Professor?
Yep, go ahead.
So if add fraction didn't have the return at the end, what would result be?
It would be none.
Okay.
So yeah, so you're saying if I didn't do this guy, so I didn't actually return it, so I build a fraction here and then just say, haha, I did it, everybody be impressed, and then don't do anything with it. Add fraction would then end. I could still do this, but result would get the value of none. So this would work, this next line, but this is going to crash it. This last line is going to crash it because now I'm trying to say none, call your display method. And there is no display method for none. But if I comment that out, now you see we have our none. So in this case, add fraction doesn't actually return a value. I am assuming he does return a value and trying to catch the value inside of a variable called result. So I get nothing because he returned nothing. And then I can print out the value of result and it is nothing. Does that make sense?
Yes, thank you.
Okay. So any questions about kind of that back and forth there of passing in parameters and what self is versus the inputs that were put in? That's something you're going to want to practice with and really trace through this code and follow it to understand the difference. Like, who is another fraction? Another fraction in this example was F2. Another fraction in this example was F4. Who is self? In this example, self is F1. In this example, self was F3. All right, so these classes are written generically so that we can have multiple fractions created and have each one of them be able to add themselves to another fraction and be able to work that way, rather than having all this stuff hard-coded in there. All right, so if you ever start seeing your variable names that live out here creep into your definition of variables that live in here, chances are you've either purposely named the variables the same because you know what you're doing, or you're relying on things that don't exist. One of those two things. All right. So having said that, let's go ahead and let's update add fraction to actually add some fractions rather than just printing numerators and denominators and things like that.
Dr. Littman?
Go ahead.
Question from the chat that I saw. Would the program still function if your parameter in the add fraction function was named something other than self?
No. So if we name that guy LOL, yeah, it's going to say this variable self was not defined. So the way Python accomplishes object-oriented programming is we need to have, so all object-oriented languages have a variable like self. A lot of times it's called this in some other languages. But the way Python handles this, because they kind of bolted on the idea of object-oriented programming, is they say, well, a class is going to require this variable self be passed in. It automatically happens. That is saying we didn't pass in a value for self here. We just passed in another fraction. So we kind of ignored that requirement for self. But what's actually happening is whoever called this function, this guy is automatically getting passed in as self at the very beginning. So this variable self is required for all instance methods. And we'll talk about the differentiation between an instance method and a class method soon. But for right now, all methods are instance methods in our world for classes. So they'll all require a very first parameter of self. So notice here that display takes no inputs, but we still had to pass in self so it knew who we were displaying. We're displaying self's numerator and self's denominator. Does that make sense?
Yep, thank you.
All right, so we go up to add fraction. Let's go ahead and gut this guy for right now, because we want to actually add some fractions together. All right, so now we have a comfort level, hopefully, or at least a more comfortable level of who self and another fraction are. So make sure you kind of walk through that and wrap your mind around that yourself. Because I realize when we go through things in class, you know, we're kind of going through pretty quickly, and I might reiterate things 4 or 5 times, but it's still, your brain is playing catch up. So go back through and, you know, prove to yourself you understand what this, how this works. And something I recommended to a student yesterday that would be a good way of practicing some of these things, and I've been mentioning this for a while, is for many of you, you probably had trouble writing this assignment or a past assignment, whatever it was. But once you see the solution, it makes sense to you. So what I suggest you do is you study that solution, make sure you understand how all the parts are working, and then go and try to write it yourself without looking at it, knowing that you have a cheat sheet. You know, because that will then kind of practice what you just learned, because a lot of you are going to have trouble right now still starting writing a function and writing that logic. But once you see the answer, it makes a lot of sense to you. All right. So for add fraction, where we have 2 fractions we're working with here. One of them is called self. That's whoever owns this add fraction. So self.numerator, self.denominator. And then the other fraction is called another fraction, who has a numerator and a denominator. All right. So what we want to do is we want to first find a common denominator. So I'm going to create a variable here. I'm going to still operate off this idea of be as verbose as you can. Don't try to take shortcuts or be fancy. Just step by step by step by step. So the very first thing we're going to need is a common denominator, and our common denominator is going to be self's denominator times another fraction's denominator, right? That's guaranteed to be a common denominator of those two guys. So we'll say self dot denominator times another fraction dot denominator. That, and we're storing that in a variable called common denominator. All right, now we need to figure out our updated versions of our two numerators. So we'll say num1, actually let's spell it out. Numerator 1 is going to be equal to, so let's say this is going to be self's, actually let's do it this way. Self new numerator. We're not actually going to change self. We're just going to store what his new numerator would be. And his new numerator will be self's current numerator times another fraction's current denominator. So we cross multiply. So we've already determined that the common denominator will be the two denominators multiplied together. So we need to scale both fractions to get to that point. So our new numerator for self will end up being self's current numerator times the other guy's denominator. And our new another fraction numerator will be equal to another fraction numerator times self dot denominator. So now we have the two updated numerators here. We have not changed the actual fractions. We did not change self's fraction. We did not change another fraction's fraction. We just created two new variables that held their updated numerators. All right, so now let's say answer fraction numerator is equal to self new numerator plus new another fraction numerator. So that's going to be our new answer fraction numerator. So now we have the numerator for our answer. We have the denominator for our answer. Now we need to build a fraction out of those. So why don't we just create a variable called answer, and we'll set this guy equal to a new fraction that is going to be our, what I call it, answer fraction numerator and common denominator. So I have a brand new fraction whose numerator will be our answer fraction numerator. And we got answer fraction numerator by adding our two adjusted numerators to each other, where we got our adjusted numerators by cross multiplying right there. And then our denominator will be our common denominator that we calculated right up top. That's going to be our two denominators multiplied together. So here's our answer. Now we want to remember that we need to return that answer. So we've done our math. We have not changed self. We have not changed another fraction, but we did ultimately create a brand new fraction with the appropriate numerator and denominator for this summation. All right. So now we can call, let's start with F1 and F2. So F1 is 1/2, F2 is 3/4. So the common denominator there would be 8, right? So we're gonna have 4/8 and 6. What is it? Yep, 6/8. So we should have 10/8 as our answer. So we'll say result.display, and there's our 10/8. If we ask F3 to add itself to F4, I don't want to do that math, but let's just trust me, this is the correct answer. It is 308/252 is the correct answer for those guys. All right, so the same generic function that we just wrote being called with multiple fractions. And nothing keeps us from, saying f1 plus f4 and getting that answer, 44/36.
So when you return something in a method of a class, does that automatically get stored as the new self?
Well, no, because self is only something that exists inside of a method. So for add fractions, self always refers to whatever fraction called this guy. At this point, when I return this fraction, I haven't used him to call any methods. So when I return answer here, it's getting stored inside of like my variable here called result. Now, when I say result.display, in that particular case, when we are inside of the display method, self will be result. So that variable self changes depending on who called the method. When f1 calls add fraction, self is f1. When f2 calls add fraction, self is f2. This return statement does not change the value of this version of self. But if I return a fraction and then later on use that fraction to call, for instance, display, like we're doing here, in that case, that guy's self is equal to the fraction that was returned before, but only because we actually used that return fraction to call his own method. So self always refers to whatever, in our case here, self always refers to whatever fraction called the method. So in this case, self would be result. In this case, self would be f1. In this case, self would be result. Self would be f3. Self would be result. Self would be f1. Does that make sense?
Yes, thank you.
All right, so now we have a generic add fraction that will add whatever self is, whoever called this method, to whatever was passed in, whatever fraction was passed in. It'll add them together and return that answer. So now we have a way of adding fractions to each other. Now notice here, just to kind of flip-flop it here, if I say f2 add fraction f1, so the first one is f1.add fraction f2. The second one is f2.add fraction f1. In this case here, self is f1, another fraction is f2. In this case here, self is f2, another fraction is f1. But we're going to get the same answer because those two fractions added together are the same answer. We just changed roles. We changed who is calling his own method. In this case, f1 called his version of add fraction, where he plays the role of self, and f2 played the role of another fraction. Where in this case, f2 called his version of add fraction, where he plays the role of self, and f1 plays the role of another fraction. All right, and again, this kind of comes down to this idea that we write this code generically. This says add whoever called that add fraction to the another fraction that was passed in. And so we've written this code generically in terms of self and another fraction. So it'll work on any two fractions. All right, now the next thing we're supposed to write is reduce. So we're supposed to be able to ask a fraction to reduce itself. So we'll have a method here called reduce. And reduce is not going to require any extra parameters. He just needs to know who called me, okay? Because we're going to reduce self's fraction. All right. Now to reduce a fraction, we need to find the greatest common denominator or greatest common divisor (GCD) of both the numerator and the denominator. That is to say, we need to find the largest value that evenly divides the numerator as well as the denominator. Okay, so if, for example, we're working with a fraction like 6/8, as a human being, we can look at this and say, well, the largest value that possibly can divide either of these is going to be the smaller of these two, right? we know that 8 will never evenly divide a smaller number. That's just not how math works. We happen to know by glancing at this that 6 isn't going to evenly divide 8 either. You know, but if we had like 832, we might say, oh, well, maybe 6 divides that guy. So in that case, the largest value that would possibly even divide both of them is going to be the smaller of our two values. So we can certainly go through the logic of figuring out which is smaller, the numerator or the denominator, or we can just decide, you know, let's just be efficient with it, and we'll just choose, or let's just be direct with it and not worry about efficiency because computers are fast. We can just say, I'm going to choose the numerator, and we'll just assume he's a smaller value. The worst that happens is we get unlucky and he actually ends up being the larger value. So maybe we have a fraction like 832 divided by 6. So 832 sixths. And now we have the numerator being a much, 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 much larger value. And it's going to take a while before we whittle it down to a value that evenly divides both, right? But computers are pretty fast, so this would be okay. But realistically, what we would do is we're going to say, for our starting point, we're just going to say starting point is equal to self.numerator. So we're going to assume that our smaller of our two values is the numerator. We might be wrong, but all this is going to mean is that we're going to check more things. We'll still get the same right answer. All right. So we decided on a starting point. Now what we want to do is we want to go from that starting point all the way down to 1. We know for a fact, again, if I have like 6/8, you know, we're hoping we find a number between 6 and 2 that evenly divide both of these. But we know for a fact that if we get all the way down to 1, 1 will evenly divide both 6 and 8, right? Okay, we know that for a fact. So we want to create a loop that's going to start off at our starting point. We're going to try to divide both of these guys by 6. Then we're going to try to divide both of these guys by 5. Then both of these guys by 4, so on and so forth. So we're going to have a for loop for I in range from starting point down to, well, we can say down to 0, so it doesn't include the 0. We can also go down to 1 because at that point we know that anything divided by 1 is itself. But let's just be explicit. We'll go down to 0, stepping by -1. All right, so now I, in our current example, the 6/8 example, the first time through I will be 6, then it'll be 5, then it'll be 4, then it'll be 3, then it'll be 2, then it'll be 1. And we happen to know that we'll have success at 1. But what we're going to do is each time through, we want to ask the question, does I evenly divide self's numerator and self's denominator? If self.numerator mod I is equal to 0, so that says if the numerator is evenly divisible by I, and self.denominator mod I is equal to 0. If both the numerator and the denominator, when divided by I, have no remainder, that means we have found a value of I that evenly divides both of them. And since we started at the maximum value that might divide both of them, we can say that we have found the greatest common divisor of both of those values. All right, so with that in mind, we're going to go ahead and update. We have our answer, so we need to update the numerator and the denominator. So we're going to say self.numerator is equal to self.numerator divided by I. And we want to use integer division, because if we use the single slash, this is going to be decimal point division, so we'll get a .0 at the end of it. So 6 divided by 2 would give me a 3.0, but 6 divided by 2 would give me a 3. We don't want to say 2 here, we want to say I. So self.numerator is equal to self.numerator divided by I, because I was our greatest common divisor. Self.denominator is equal to self.denominator divided by I. So we've updated this guy's numerator and denominator. We have changed this fraction. Okay, we actually changed his value. So this fraction is now a modified version of himself. We have nothing to return. We have actually modified self's numerator and self's denominator. All right, so now we're done. We don't need to check any more versions of I. So we want our method to immediately end. And you remember, we talked about the return keyword. The return keyword does two things. It ends a function and then optionally will return a value. I don't want to return a value here, but I do want my function to end. So that will kick me out of the function by saying return. So now I have my, let's just operate off of our first one here. So I'll display result. Then I'll tell result to reduce himself. And then I'll tell him to display himself again. So the first time through, we'll get a 6/8. So we display 6/8. Then we ask result to reduce himself, which we just saw will change him. And then we'll tell him to display himself again. And now we'll get our 3/4. Oh, I'm sorry. I had 6/8 from our other example. So we had 1/2 plus 3/4, which was 10/8. So now we have 10/8 and we have 5/4, the reduced version of 10/8. Does that make sense? All right, so let me show you a problem here. I'm going to import random. And here I just need to remind myself. The rand int. What's my random number? Okay, rand int. It takes some parameters. So I could say, give me a random integer between 1 and, is that 1,000,000? Random.randint. Imported random. All right, it's weird that I didn't just have access to it, but that's fine. So random.randint will give me this some number between 1 and 1,000,000. So now what I can do is I can use this guy to create a fraction that has a randint between 1 and 1,000,000, a randint between 1 and 1,000,000. So presumably these are going to be really big fractions. And actually, just before I forget here, let me just paste this solution into $200. Make sure you have that before I start doctoring this code. Random.rand int to 1,000,000. So now we're going to create crazy fractions, really large fractions. So we'll go ahead and tell F1 to display itself, and we'll tell F2 to display itself. Then we'll add the two together. And here, before all right, so here's what F1 is, here's what F2 is, and then here's those two fractions added together. Really big numbers, right? So now I'll call reduce, I'll call display, and we're waiting. This program is not finished running yet. It's waiting, you know, it's going through trying to reduce this fraction using our, let's call it, uninformed version of reduced fraction. We know that our version of reduced fraction here accurately reduces a fraction. But how are we making it work? Well, we're starting with this value right here and trying to well, going from this value all the way down to 1, asking, does this number and this number evenly divide that current value? Well, what is this value? So that's that's 100,000. This is 484,266,813,959. That's a lot of numbers to check, right? And notice it's still running. I bet you that there's a decent chance we can leave this running and it'll still be going by class on Friday. So it will not have finished. So what we have right here is something called a time complexity problem. All right, so time complexity problems are accurate solutions that take too long to run. And the reason I like to look at this through the lens of fractions is that in a fraction feels like it's a pretty simple thing. It's just a numerator and a denominator. And reducing a fraction seems like a pretty simple thing. You just find the biggest value that evenly divides both the numerator and the denominator. And that works fine for reasonable size fractions, probably fractions that we would normally bump into. But in this case, we've created unreasonable size fractions. And since we have unreasonable size fractions, we're noticing that our particular approach, that uninformed approach to reducing that fraction for finding the greatest common divisor of those two fractions is causing a problem for us. Okay, so there is often we'll call it a mathy alternate solution to the problem that greatly improves its speed. All right, and by the way, this guy's still cooking. He's still running, still trying to divide numbers, just going at it. And remember, I've made this argument over and over and over again that our computers are really, really, really fast. Okay, and this computer has, I don't know, 16 i9 cores in it, so it's a fast computer that I'm running on right now. Okay, so there's often a mathy alternate solution to some of these problems. Now, there exists an algorithm. So we'll just put in here by our example. Example, reducing fractions. Let's call this brute force reduction takes too long for very large fractions. The Euclidean algorithm also known as GCD function, greatly reduces this time. Now, we don't have to invent this guy. Some smart mathematician out there came up with the Euclidean algorithm for us. I usually use the one from Wikipedia, but oh, I have Python in there, that's why. So this guy goes through and it explains the whole Euclidean algorithm and how the math works and all that stuff. So I encourage you to read through that for educational purposes. But down here near the bottom, they're going to give you the mathy function for it, or the codey looking function for it. So we'll call this pseudocode, all right, because it's not written in any particular language, but they say, here's a function called greatest common divisor that will take in two parameters. This is the numerator, this is the denominator. And as long as in this case, b, so it doesn't matter which order you pass. You could pass in the denominator and the numerator here. So this takes in two integers and it's going to return the greatest common divisor of those two integers, the largest value that evenly divides both of them. All right? So as long as b is not equal to 0, we're going to create a variable called t instead of equal to b. We're going to preserve the value of b. Then we'll update the value of b to be a mod b. So this is integer remainder, so the percent symbol. And then set a equal to the old value of b, which we preserved in t. Do this over and over and over and over again until b is finally equal to 0. And then our final answer is a. So our final answer here is the whittled down version of a, which will be the greatest common divisor, the greatest number that evenly divides both a and b, the original a and the original b. All right. For us, it's not important that you understand the math. That's what all this stuff is up here. Some, really smart guy, the guy who invented geometry, among other things, has come up with this for us. All right, the Euclidean algorithm that gives you the greatest common divisor of two numbers. So for us, what we want to do is we want to modify our program to use this approach for figuring out the greatest common divisor of our numerator and our denominator, rather than our current approach, which checks every single number. And I think you'll see that for this exact same code, you get a substantially better, a substantially faster result, in that you would have gotten almost an instantaneous result. All right, so I'm going to give you this code as a starting point. So our homework update our reduce function to use the Euclidean algorithm. There's a link to where you can find it. To greatly reduce the speed, or greatly reduce the time it takes to run for very large fractions. I'll give you an extra little hint here. You might decide to write the Euclidean algorithm as a function that you can just call whenever you need the greatest common divisor 2nths. All right, so I'll give you this code as a starting point. I'll put this homework assignment up. It's due on Friday. Any questions, comments, concerns? So at the end of the day, you're going to convert this pseudocode into Python, put it in a function, and then use it from your reduce function. Okay, it should not be a lot of code. You're just going to have to think through the process of how to use these pieces. All right. All right. I will see everybody on Friday. I'll hang out for a few minutes in case anybody has any questions. Otherwise, hit me on Slack, or if you need to meet, always show up to the Bitwise Bar and Grill for happy hour, usually 6:30 at night. Otherwise, I will see you on Friday.
Thank you. Have a good day.
Yep. Take care.
Bye.
Thank you.